6.1 is a review of trigonometry. A lot to review. This is a repetition of your Math 1300 class. So in 1300 you did chapter 6. We're repeating chapter 6 one more time. I believe you did section 6.1 to 6.5. I'm going to go over those, skim over them quickly. So I need to remind you really quick how this works. A standard angle is what we start with. So we're going to be using standard angle all throughout this course. An angle is said to be in standard position if its vertex is along the origin and its initial side coincides with the positive x-axis. So a polar grid looks like this. If you really want to map it on the rectangular coordinates, you can. It looks like this. At 0 degrees, I'm right there. Of course, this is going to always be positive rotation. This is going to always be negative rotation. Now, I don't have any examples. I'll be asking if you want to do examples to do more in class, but for now, I'm going to go over some of the theory. And keep in mind, given a right triangle, again, a quick refresher, you should have taken this in trig, and if you don't remember it from trig, you should have reviewed it in your previous course. So this is 6.1 that you already covered in your previous class. If you pick an angle, the side opposite of that we refer to as O for opposite. The side that's opposite of the 90 degrees is the hypotenuse. We refer to that as H. And the side that's not labeled, besides the opposite and the hypotenuse, we label as the adjacent. Associated with any right triangle are 6 trigonometric functions. There is the sine of that theta, the cosine of that theta, and the tangent of that theta. Sine is the ratio of the opposite over the hypotenuse. Cosine is the ratio of the adjacent over the hypotenuse. And tangent is the ratio of the opposite over the adjacent. Cosecant of theta is the reciprocal of sine. It's really the hypotenuse over the opposite. Secant of theta is the reciprocal of the cosine. It's the hypotenuse over the adjacent. And cotangent of theta is the reciprocal of the tangent. Also, actually, I'll get to it when I get there. So for now, this is what we have. So if I rotate starting on the positive x-axis, a very important angle is the reference angle. What I'm trying to do, I'm trying to mimic this triangle in all the quadrants. We say, let theta be denoted as an angle that lies in any quadrant. The acute angle means it's an angle between 0 and 90 degrees. It's never negative, and it can never exceed 90 degrees. It's formed by the terminal side of this angle theta and the x-axis, always the x-axis. So I could be in any quadrant, and I'm going to tackle all quadrants. Suppose I rotate and theta, I stop in quadrant 1 somewhere. So I have this side. I'm supposed to be on the positive x-axis. I rotate and I stop right there. So this is the terminal side of the angle theta. I'm going to run from that side straight to the x-axis, create my rectangle. My triangle. This is the radius. This is the x. This is the y. If I rotated and I happen to be in the second quadrant, if this is theta, then the reference of theta is really the side associated with where you stop. You run from that side straight to the x-axis, and this right here is the reference angle of theta. If I happen to rotate and I'm in quadrant 3 for some reason, if theta happened to be right there, then that's the terminal side of theta. I'm going to run from that angle to the x-axis, and this right here would be my reference angle, always positive. And if I happen to rotate an angle and I'm in quadrant 4, let's say that's theta, so the terminal side associated with theta is right there, and I will run from that angle to the x-axis, forming a triangle. That's always x, that's always y, that's always r, and that's always the case. So I could use the reference angle all the time to talk about theta in certain conditions, and let me get those conditions out of the way. Given a circle, if I happen to have a circle with radius r and a central angle. What's a central angle? It's an angle that's centered at the origin or at the center of the circle. This is r. If I rotate some angle theta, this is also r. So two things that I need to remember. If I take this arc, call it S. If I want to know what the length of S is, that is the radius times that angle theta. And if I want to know what this area is, and we need to know both of those, if I want to know what that area is, they call it area of the sector. That is 1/2 r squared times theta. What's the catch? Theta must be in radians. And now to put everything together, if I consider a unit circle, and if you recall what a unit circle is, that's a circle in which the radius is 1. Then S will equal r times theta. That's really 1 times theta. That's theta. So what does that tell me? That tells me the arc and theta are identical if I am in radian mode. So in quadrant 1, if I let the radius be 1, quadrant 2, quadrant 3, and quadrant 4, right? If I'm thinking of this as a circle, I know it's an odd looking circle. In which the radius is 1, then I could say, you know what? Instead of talking about this theta, I could use the reference angle to really match that. Because whether I'm on the outer circle or this theta, it's the same, because theta and S are identical. So I'm going to make use of this if I have a unit circle. I could really make use of a lot of things. And let me start with the first one. So consider a unit circle. Here I am. I have a circle with a radius of 1. Oh, that's not centered. That's why it's kind of off. Still not centered. A bit to the left. Just a bit. Got it. Okay. So if I pick a point, any point, let's say that point. Again, this is a unit circle. Well, if I run from the origin, create my rectangle, there's x, there's y, that's 1, there's theta. We agreed that the sine of this angle theta is the opposite over the hypotenuse. That's y over 1, which is y. The cosine of theta is the adjacent over the hypotenuse, which is, hey. So instead of saying x and y, I could say that's the same thing as cosine of theta and sine of theta. Meaning, I could take this out and say that's the cosine of theta, take this out and say that's the sine of theta. And if I'm looking at this right triangle, I know that tan of theta is the opposite over the adjacent. And I also know that if I take this side squared plus this side squared, that is 1 squared. Hey. And if I divide everything by cosine, cosine over sine, well, if tan is sine over cosine, then I know that cotan of theta is the cosine of theta over sine of theta. So if I divide everything by cosine squared over cosine squared is 1. Sine over cosine is tangent. And 1 over cosine, we said that was the secant. And if I go back to this and divide everything by sine squared, cosine squared over sine squared is cotangent squared. Sine squared over sine squared is 1. 1 over sine squared is cosecant squared. Those are called the Pythagorean identities. So there are many identities you're supposed to know. The sine of 2 theta is twice the sine of theta cosine of theta. The cosine of 2 theta happens to have 3 identities. It's either cosine squared of theta minus sine squared of theta. It is twice the cosine squared of theta minus 1, or 1 minus twice the sine squared of theta. If I take this and solve for cosine squared, I'll get the power reduction identities. The cosine squared of theta is 1 plus the cosine of 2 theta divided by 2. If I take this equation and solve for sine squared, I will get sine squared of theta is 1 minus the cosine of 2 theta divided by 2. You really don't have to worry much about half angles, but you need to know this on the long run. And if I remember as well, I remember a very important angle is the coterminal angle. Coterminal angles are 2 angles that share the same initial and terminal side. You could take any angle that you like, add 2 pi or 360 degrees. So if this is an angle theta, guess what? This angle is coterminal to it, and this angle is coterminal to it. So if I take an angle theta, I add 2 pi or subtract 2 pi, I will get a coterminal angle. All what it means, you remain on the same position, no matter what that angle is. And of course, the most important to remember, all students take calculus. All the trig functions are positive in quadrant 1. Only the sine is positive in quadrant 2, which means cosine is negative and tan is negative. Only tangent is positive in quadrant 3, which means sine and cosine are negative. And cosine is the only positive trig function in quadrant 4, which means sine and tangent are negative. Associated with this would be 2 right triangles for you to remember. I don't know how well you remember those, but you need them all throughout. One is a 30. Automatically that makes this a 60. So you start with the side opposite of 30. If that's a 1, the hypotenuse is 2 and this is radical 3, and an isosceles triangle in which this is 45 degrees, that makes this automatically 45 degrees. If this is 1, this is automatically 1, and that's a radical 2. So that pretty much solves most of what you need, along with you remembering that if I have a unit circle, this point right here is 1, 0. This point right here is 0, 1. This point right here is negative 1, 0. And this point right here is 0, negative 1. So along with all of that, you should be able to figure out almost what's needed. You remembering this and those two. And the magic number is that if you rotate one full revolution around the circle, that's 2 pi radians, and that's also 360 degrees. If you divide by 2, this is the magic ratio. And if I want it out of those, if I divide by 180 both sides, backwards. If I divide by pi both sides, I'll get 1 radian equal 180 degrees divided by pi. If I throw that in my calculator, that's roughly 57 degrees. So this is a quick refresher on trig. Just thinking if I left anything out. Now, in our meeting tomorrow, I will go over examples. I'll show you the book and you can pick any examples you want. And I'm going to list the homework at the end of this as well.